So this is high surface tension. So you have to know that water has hydrogen bond, and at the end it has high surface tension until certain insect can walk on the surface, the water surface. So the first point, they say water has a high surface tension. That means you look at the picture here, because of hydrogen bond, they are like stick to the water molecules at the bottom, making the molecule to go downwards overall, and making the surface has a lot of water molecule, and that is the surface tensions. Okay. So surface tension is the ability of a liquid surface to resist any external forces. Example, to stay unaffected by forces acting on the surface. So that is surface tension. Okay, so it's something very close to a solid. Solid is where the surface has so many atoms until they can have resistive force. Okay, resist you from pressing it. So the water molecules at the surface of liquid are bonded to other water molecule through hydrogen bonds. Okay, so because of hydrogen bond, you have water surface, you have surface tension. These molecules pull downwards on the surface molecules, causing the surface to become compressed and more tightly together at the surface. So this is the main idea. So hydrogen bond causes the molecule to pull downwards, then the surface molecules have more molecules that hold tightly together, and this is the surface tension. So let's move on. Okay, density. Okay, so the special properties of water is where the density of ice is lower than the density of water. So ice float, solid form float. That is rare actually. Now, first point you can see solids are denser than their liquids, as the particles in solid are more closely packed together than in their liquid state. So this is the normal situation. Normal situation, solid are denser, but in ice, the water molecules are packed in a 3D hydrogen bonded network in a rigid lattice. So which means like this. Okay, so you can see there are open space here because of the hydrogen bonds. They need to bond in a particular direction, so that there are empty space formed in between and making the ice to be less dense. So the more open structures of molecules in ice causes it to have a lower density than liquid water. So because of this empty space there. Okay, so each oxygen atom is surrounded by hydrogen atoms. So you can see the blue one is the oxygen atoms and is surrounded by hydrogen atoms. And then this way of packing the molecule in a solid and the relatively long bond length of the hydrogen's bonds, okay, you can see long bond length, means that the water molecules are slightly further apart than in the liquid form. So because they are further apart, they are less dense. Therefore, ice has a lower density than liquid water. Okay, so let's see the exam tips here. So they say ice floats on water because of ice lower density. So it has lower density. Okay, let's move on. Okay, so this is the starting of the van der Waals forces. Hydrogen bonds finish already. So polarity and dipole moments. So what is polarity and dipole moments? Of course, you can see here. So they start with electronegativity, which is the ability of an atom to draw a pair of electrons toward itself in a covalent bond. So it's something like this. the electrons in the covalent bond. So if it is electronegative, it will pull closer to the atoms. That is more electronegative. So electronegativity increases across a period. That means when you go across the period to the right, electronegativity increases and decreases going down a group. That means if you go down a particular group, let's say group 1, the electronegativity decreases. That's the trend. And we look at what is polarity here. When two atoms in a covalent bonds have the same electronegativity, the covalent bond is non-polar. This is non-polar. This is non-polar because this and this has the same electronegativity, and hence the bonding electrons are shared equally in the middle. They don't have any delta minus or delta plus. Okay, it doesn't happen in this molecule, so we call this molecule to be a non-polar molecule, and we call this covalent bond as non-polar bond. Okay, so let's move on. Okay, here, when two atoms in a covalent bonds have different electronegativities, the covalent bond is polar, and the electrons will be drawn towards the more electronegative atoms. So this is the example, HCl, where chlorine is more electronegative, so the bonding electron will be attracted more towards the chlorine. So it's going towards the chlorine and making chlorine to be a bit more negative, and hydrogen is on the other hand a bit more positive. So this is the polarity of the molecule. So the covalent bond is polar bond, and then the molecule is polar molecules. Okay, now as a result of this, the negative charge center and positive charge center do not coincide with each other. Okay, so this means that the electron distribution is asymmetric. So that means not evenly distributed. The less electronegative atoms gets a partial charge of delta positive. So here, the more electronegative atoms get a partial charge of delta negative, which is here. The greater the difference in electronegativity, the more polar the bonds becomes. Okay, so this becomes more polar. So one extra thing to talk about more polar is when they are more polar, they will have more ionic characteristics. Like for example, can dissolve in water, as in HCl, that it can dissolve in water because it is polar. Okay, then what is dipole moment then? It is very related. So the dipole moment is a measure of how polar a bond is. So if the bond is very polar, the dipole moment will take a greater value. So the direction of the dipole moment is shown by the following sign, in which the arrow points to the partially negatively charged end of the dipole. So that means from positive to negative, from delta positive to delta negative. So the sign shows the directions of the dipole moment, and the arrow points to the delta negative end. So this side is delta negative. Okay, so for example, let's say if I have this HCl up here, so the dipole moment is drawn in this way. Okay, so that is dipole moment. Let's move on. Assigning polarity of molecules. So to determine whether a molecule with more than 2 atoms is polar, the following things have to be taken into consideration. The polarity of each bond, how the bonds are arranged in the molecule. They are trying to say that they are trying to say one problem here. Polar bond sometimes leads to polar molecule, sometimes lead to non-polar molecule. So what am I trying to say is, if you have polar bond, it doesn't mean that the molecule will be polar. Sometimes it can be polar. For example, HCl. So it has polar bond and the molecule is polar, which is delta plus and delta minus here. Okay, that is polar bond, and at the end we have polar molecule. Example, HCl. Okay, so but sometimes we have polar bond, but at the end the molecule is non-polar molecule. Normally it is because of symmetry structures, like symmetry structure like tetrahedral, trigonal planar, like linear. Okay, you see I'm talking about the 4 sigma bond with no lone pair, 0 lone pair, and then the 3 sigma bond with 0 lone pair, if you still remember that, and the 2 sigma bond with 0 lone pair. There are more actually. They are like the bipyramidal, So this is the 5 sigma bond with 0 lone pair, and the octahedral, the 6 sigma bond with 0 lone pair. So all these structures, right, are symmetry structures. So if they are symmetry, meaning that at the end they will become non-polar molecule, and that is basically because the dipole moments are cancelled off. Okay, are cancelled off. So let's start with the easier one, linear. Linear. So let's say for example, carbon dioxide. So if you want to know whether this covalent bond is polar bond or non-polar bond, it's very easy to decide. If there are different elements, then they are polar bond. So this is polar bond. Okay, polar bond. So these two are polar bond because oxygen is more electronegative than carbon. So they have polar bond. So they have polar bond, and at the end it has linear structures where the dipole moment cancel off each other, and at the end it is non-polar molecule. Okay, non-polar molecule. So how they cancel off, imagine it's something like the dipole moment for this cancel off by the dipole moment over there. They are like cancel off. Okay, so they are acting in opposite direction and hence cancel off. Okay, so something like physics, like physics. Let's say you have an object. If somebody pull it 5 Newton to the right, another Newton pull it 5 Newton to the left, then they cancel off and 0 resultant force. Something like that. Okay, so the dipole moments are cancelled off in all these situations. Okay, so let's say one more example. Let's say trigonal planar. Let's say I take BF3. Polar bond actually. Okay, because boron and fluorine have different electronegativity, so they are polar bond, and then at the end the dipole moment are cancelled off because all these are symmetrically distributed, and at the end the molecule is non-polar molecule. So you have to make sure you get the idea on this. Okay, now let's come back to the words here. How the bonds are arranged in the molecule. will determine whether it is polar molecule or non-polar molecule. Basically, it's easy to decide. When there is no lone pair, then it's non-polar. When there is lone pair, then it's polar molecule. Okay, so some molecules have polar bonds but are overall not polar molecule because the polar bond in the molecules are arranged in such way that the individual's dipole moments cancel each other out. This is what am I trying to say just now. They cancel out. So they cancel out in all these situations. Okay, and let's move on. Okay, so now they give example. Okay, this one, it has a dipole moment. So why? Although this is tetrahedral, it is first it has polar covalent bonds. Okay, it has polar covalent bonds. And after that, this CCl is a more polar compared to this, and this. So the overall dipole is towards the electronegative chlorine atom. Okay, so it's like this one pull, the dipole moment is here, and this one is up. So overall it's like going up. So it is a polar molecule. Okay? So they cannot cancel out as in here. This one they cancel out because all these are the same dipole moment. Okay, but this one different. So you can see something like this. This is tetrahedral. This is also tetrahedral. Tetrahedral with same terminal atoms cancel off. Tetrahedral with different terminal atoms, they cannot cancel off. So this is polar, this is non-polar. So the dipole moment cancel each other out for this case. Okay, so remember, although I said just now tetrahedral will be non-polar, but be careful. The extra condition is the surrounding atom must be the same. If the surrounding atoms are not same, then they fail to cancel off also. Okay, so now we have the van der Waals forces. Okay, van der Waals forces is very much affected by the polarity of the molecules. So let's see how. So covalent bonds are strong intramolecular forces. So intra, do you know what is intra?
Is it like within the molecule?
Yes, within the molecules, yes. Okay. So inter, what do you think? What is inter?
Is it between like two or more molecules?
Yes. The between the molecules, that is inter. So covalent bond is intramolecular forces, and the van der Waals forces is the intermolecular forces. Okay, so the intermolecular forces are called van der Waals forces. There are two types of van der Waals forces. The first type is the temporary type. The second type is the permanent type. The name is quite long. The temporary type is known as Instantaneous Dipole Induced Dipole Forces, also known as London Dispersion Forces. So normally we take this name, Instantaneous Dipole Induced Dipole. Okay, so this is the second type, which is known as Permanent Dipole Forces. It's a long name again. You have to write this twice. Permanent dipole dash permanent dipole. Okay, so let's see example. The polar, okay, you see here, the picture here. The polar covalent bonds between O and H atoms are intramolecular forces. That means this one, intramolecular forces. This is the covalent bond. and they are called polar covalent bonds. And the permanent dipole forces between the molecules are intermolecular forces. So this is intermolecular forces. So this is hydrogen bonds, of course, hydrogen bonds, a special types of permanent dipole. So permanent dipole happens when the molecules have delta positive and delta negative. Then permanent dipole happens. But if let's say the delta positive is because of hydrogen, the delta negative is because of FON, and then it is a special type of permanent dipole, which is hydrogen bond. Okay, so if it is not between that two, then it's just the normal permanent dipole, which is under the van der Waals forces. Okay, so let's see. Okay, first we understand instantaneous dipole, induced dipole. Okay, so instantaneous dipole, induced dipole forces or London dispersion forces exist between all atoms or molecules. So all atoms, no matter they are polar molecule, non-polar molecules, they all have instantaneous dipole, induced dipole forces. Okay, so that means they have van der Waals forces. There's this type of van der Waals forces. So how these forces is formed, we need to understand it. So they say the electron charge clouds in non-polar molecules or atoms are constantly moving. No matter they are non-polar or polar, the electrons are just keep moving everywhere. So at one particular moment, they will have more electrons here and less electron here, and making here more negative for temporarily, making here more positive for temporarily. So there is a temporary dipole. And this temporary dipole make what are they trying to say here? Okay, hold on. I scroll down a little bit. As the instantaneous dipole approaches the non-polar molecules, it induces a dipole in the neighboring non-polar molecules. So that means it is affecting the neighbor. So you see how they affect the neighbor. So when these molecules have delta negative and delta positive for temporarily because electrons are more here, then it will make the neighbor having the polar molecule as well, where if here negative, right, it will pull away the electron to the other side. Okay, then making here positive, hence they attract. And this is the Idid forces. Okay, so yeah, that is how it works. So you need to know first, we have this because the electron distribution is not evenly distributed, as they are freely moved, so at one particular moment one side has more electrons, and then it affects the neighbor, making them having some polar properties, and then it attracts. Okay, so that is the Idid. Okay, let's see the information here. You can see first is the electron charge cloud, which are constantly moving, and then the electron charge cloud can be more on one side, causes temporary dipole, this one, and then the temporary dipole can induce a dipole on neighboring molecules, so which is this situation. Okay, induce the neighboring molecules. So when this happens, the delta positive end of the dipole in one molecules and the delta negative end of the dipole in a neighboring molecule are attracted towards each other, so which is here attracting, and that is the temporary dipole. so let's move on. Okay, let's see. Idid forces increase with increasing number of electrons in the molecule, and atomic number, okay, that means proton numbers, increasing the places where the molecules comes close together. Okay, so the main factor is this one, number of electrons. So if it has more electrons, basically the Idid forces is greater. Okay, so this one increasing the places where the molecule come closer together. This one is depends on the structures. Okay, depends on the structures. So for example, let's say between a structure which is long and a structure which is round. Okay, so what we can say is if they are long shapes, then they can form more Idid forces. If they are round shapes, then they can form less Idid forces. Okay, so example is like butane. Butane, CH3, CH2, CH2, CH3. They are long, okay, so they can form a lot of Idid forces. Compared to this round shapes, for example, it's like C with CH3, CH3, CH3. So this one round shaped. Okay, or maybe I put one more here, then it looks more round. So in this situation, then the Idid has less places to form. As in here, you can see less surface area in contact, in other words. Okay, now next one. Going down the group, the Idid forces increase due to increased number of electrons in the atoms. So you can see here. Okay, so this is going down group 18, noble gases. So the Idid forces is getting greater, and hence you need more energy to vaporize. Vaporize means to change from liquid to gas. Okay, so you need more energy to make that to happen, and boiling point is increasing. Okay, next one. So this is what I mentioned just now. This one is like linear shapes, so more places to form the Idid forces. This is pentane. This is the one that is spherical shapes. So spherical shape, there are less contact points, so hence it has lower boiling point. This one higher boiling points. So the shape of the molecules affect. Okay, so but remember the main factor is still the number of electrons. So the shape is the secondary factors. Okay, so we can use these secondary factors normally when they have the same number of electrons. If you go and count the number of electrons of this and this, they are the same, because basically these two are C5H12. This is also C5H12. So same molecular formula, same number of electrons. So if electrons is the same, then you look at the secondary factors, which is the shape of the molecules. Okay, so now permanent dipole, this is PD. It happens to polar molecules. Compared to just now the Idid, Idid is happening on polar molecule as well as non-polar molecules. But this one only happens in polar molecules. So polar molecules mean it has delta positive and delta negative. It can have negative and positive end. So the forces between the molecules that have permanent dipole are called permanent dipole forces. And what happens is the delta positive will attract the delta negative end of a neighboring molecule. So example, let's say HCl. Here delta negative, here delta positive. So it attracts with another HCl. Delta positive, delta negative. So it attracts here. And the attraction is permanent. That means 24 hours attracting. Okay, so let's move on. This is the example. So delta negative attract by delta positive. For a small molecule with the same number of electrons, PD forces are stronger than ID. So there are conditions. Must be same number of electron and small molecule. Then this will be stronger. Okay, so for example, butane and propane have the same number of electrons. Sorry, butane and propanol, same number of electrons. So this is butane, this is propanol, same number of electrons. Okay, butane is a non-polar molecule. This is non-polar, and we have ID forces. Just ID. Propanol is a polar molecule, and we'll have PD forces as well as ID forces. You know, ID forces is happening on all kind of molecule, no matter it's polar or non-polar. So I add here and ID forces. So obviously this is the stronger in intermolecular forces. First it has two types. Okay, so it has two types, and then therefore more energy is required to break the intermolecular forces between propanol molecule than between butane molecules. So propanol has a higher boiling point than butane. So because there are more intermolecular forces, and some of this is stronger than this one, so that's why boiling point is higher. Okay, now let's see exam tips. Remember this difference: intramolecular forces, this is covalent bond, are forces within a molecule, whereas intermolecular forces are forces between a molecule. So let's say I ask you, just to check on it, intermolecular forces, covalent bond, intermolecular forces, van der Waals forces, who is stronger between covalent and van der Waals?
Covalent bond.
Yes, covalent bond is stronger than van der Waals forces. Okay, let's say covalent bond and hydrogen bond, who is stronger? What do you think?
Is this still covalent?
Yes, still covalent. Okay, so covalent bond is stronger than intermolecular forces.
Okay. Wait, so
yes,
is hydrogen bond under van der Waals, or is it just like a separate type of bonding?
It is separated types.
Okay.
It is not under van der Waals. Okay, so although just now the note say it is a special type of PD forces, but we have to put it in different groups. Hydrogen bond and van der Waals forces are two different types of intermolecular forces. Okay, so now hydrogen bonding as a permanent dipole. Okay, so it's a special type. Okay, it's a special type. So that's why hydrogen bonding is intermolecular forces. It is a permanent dipole forces. Okay, so but this is the stronger one. Okay, the stronger one compared to the van der Waals forces. The permanent dipole in van der Waals forces, this is stronger. Okay, so what happened is the hydrogen which bonded to O and N, the hydrogen is very positive. The O and N itself is very negative. So that's why the hydrogen bond is stronger. Okay, so it's stronger. And now let's move on. So we are now comparing bonds to intermolecular forces. So let's see. Intramolecular forces, which is within a molecule, we have ionic bonds, which is electrostatic attraction between positive and negative ions. We have covalent bonds, where they share electron, two atoms share the electrons. We have metallic bonds, which is electrostatic attractions between the metal cations and the delocalized electrons. So we have three types of intramolecular forces: ionic, covalent, and metallic. Okay, so this is the example. This is ionic, this one covalent, and the next one is metallic. Okay, so this is metallic. Okay, now intermolecular forces. Intermolecular forces, we have permanent dipole. We have hydrogen bonds. We have instantaneous dipole, induced dipole. So three types of intermolecular forces. Okay, so these and these are under van der Waals, and this is not under van der Waals. Okay, so they show the same picture again. This is PD. This is ID. Okay, so let's move on. And again, they show the same pictures. This is induced dipole, instantaneous dipole, induced dipole, all this. This one is hydrogen bonds. Okay, now let's compare. In general, the intramolecular forces are stronger than intermolecular forces. You see the intermolecular forces stay at the lowest part, which is the weakest part. Okay, covalent, ionic, metallic. Metallic is the strongest. So this is the arrangement in terms of strength. So it is like that. And let's move on here. Dot and cross diagram. So dot and cross diagram, we already learned that is the arrangement of electrons in the outer shell. That means valence electrons. So in ionic or covalent, we can draw dot and cross diagram. So for example, ionic. So how we draw? Remember, put square bracket with charge outside. Positive charge, negative charge. Okay, then example again, magnesium oxide. Magnesium oxide, this, put charge here. Calcium fluoride, you can see we put the charge here. So 2 fluoride. Okay, so these are how we draw the cross and dot diagrams for ionics. Then for covalent, so how we draw, you can see the sharing of electrons over here. Okay, share electrons. So this is single bond, this one double bond, this is triple bond, this is single bond with lots of lone pairs. So sharing electrons, HCl. All these are covalent molecules. So the way that we draw the cross and dot diagram is different. No square bracket is found here. So you can also see double bond and double bonds for this carbon dioxide. Okay, and more pictures. So you can see ammonia. Okay, ammonia, this is ammonia with a lone pair here, and then this is water, H2O, and then this is methane. Methane is CH4. All these are covalent, and they show more covalent bonds, covalent molecule. Okay, so this is ethane. This one is ethene with a double bond here. So that's why 4 electrons there. And then we have the hydrogen cyanide, HCN. So it has a triple bond here. Okay, so triple bond over here, and then single bond here. Okay, so then coordinate bonding. So of course we learned this already. This is like comparing the bond only. They put together to compare. Coordinate bonding is like there is one atom that provides both the electrons, another atom that receives both of the electrons. So you can draw an arrow to represent coordinate bonding. So you can see here, it happens to ammonium ions. So this is where the arrow is shown, dative covalent bond. So the nitrogen here has the lone pair, as you can see, lone pair that are given to the hydrogen ions. So that's why the arrow is pointing towards that side. Okay, then this is another example, the dimer, aluminum chloride and another aluminum chloride, they form dimer, which is Al2Cl6. So you see how they form the dative bond. One dative bond is here, okay, this one, another dative bond is here. Okay, so there are two dative bonds that hold them together, so we use arrow. And then we have incomplete and expanded octet rule. Okay, so this is the expanded octet, PF5, 10 electrons here. So this is another expanded octet, PCl5, 10 electrons there. So why they can take 10? Because phosphorus come from period 3, can use 3d orbitals. And then let's see this, SF6. So again, this is expanded octet. As you can see, 12 electrons. This one, sulfur dioxide, 4 and 4 and 2. 4, 4, 2, that is 10. This is expanded octet as well. Okay, so okay, let's see this one. Now we have incomplete octet. So you can see here, boron 2, 4, 6, 6 electron. That is incomplete octet. Octet must be 8, right? So this is just 6. Sometimes we have special scenario, odd number of electrons. For example, nitrogen monoxide. This nitrogen monoxide, right, no matter how you try, if you have one left here, so that will be the special scenario. We have one here. Normally they come as lone pair, lone pair, lone pair, but this one no choice. Double bond and odd number of electrons here. Okay, so finish.